Good to see you here. Okay, so I will talk about intelligent computational agents that require a designer. So I'm the director of the Center for Innovation in Research in Computing and Research in Computing here at Southern Adventist University. Here you can see a good group of students working on different research projects, projects related to software engineering. So we develop software with Mr. Sigurd Meyer, who is also here. He's our senior software developer. So we develop software for industry, for the church, at different levels, General Conference, North American Division. We also do research in computer science. So let's start. Maybe you have heard about the game of life. Have you heard about the game of life? Okay, I will explain what the game of life is. This is the picture of John Horton Conway, who was the inventor, the creator of this game of life. So this is the idea of the game of life. Initially, you have a grid, two-dimensional grid, a very simple one, just like this one at the left-hand side. And then, by applying some basic rules, you can see how the population grows or shrinks, okay? So keep these ideas in mind. Also keep this in mind. These are the basic rules of Conway's game of life. Okay, very basic ideas. We have four rules, basic rules. The first rule, a living cell, so you have different cells here. So a living cell living cells die if they have fewer than 2 neighbors. So for example, this blue one dies in the next generation because it just has one neighbor. Second rule, living cells die if they have more than 3 neighbors. Okay, so you have 4 neighbors here and 1 blue cell here. So in the next generation, this blue cell just dies. Okay, simple. Next rule. Dead cells that have 3 neighbors become alive. This is a rule for reproduction. Okay, so you have 3 cells like this, and then you see in the next generation something like this, a new cell that becomes alive. And finally, we have something like this. Otherwise, there is no change whether cell is alive or dead. So in any other case, you see that the state is the same in the next generation. Okay, so keep this in mind, these basic rules in mind. So these rules are related to what Stephen Hawking and Leonard Bloodinow explain or say in the grand design. Take a look at what they say. The example of Conway's game of life, so the game of life that we just saw, shows that even a simple set of laws can produce complex features similar to those of intelligent life. As in Conway's universe, the laws of our universe determine the evolution of the system given the state at any one time. This is deep and related to computer science and life. So, according to Hawking and Bloodinow, pre-existing physical laws are responsible for the complexity observed in intelligent beings. Pre-existing physical laws. However, can even simple laws, just as the laws in Conway's game of life, just 4 laws, be generated fortuitously, just by chance? What do we learn about laws, design, and complexity from the world of computation? So I will answer that question in this presentation. Okay, so this is the agenda for this presentation. First of all, I will present the idea of intelligent computational agents. Then I will talk about agents in deterministic and stochastic contexts. And I will explain these concepts related to artificial intelligence, machine learning, genetic algorithms, dynamic adaptation of systems, and I will finalize with a conclusion. Bible-based conclusion. So, artificial intelligence, we live in the era of artificial intelligence. In the news, movies, everywhere you read about artificial intelligence. So artificial intelligence is not new. Artificial intelligence was formally established in the 1950s. So a good definition of artificial intelligence is found here with McCarthy, one of the fathers of artificial intelligence. Artificial intelligence is the science and engineering of making intelligent machines. Machines that exhibit somehow a certain level of intelligence. So here you can see an intelligent agent that receives as an input abilities, goals, prior knowledge, and so on. This agent applies or carries out actions on the environment, and then this environment or these actions that are applied on the environment are used as past experiences to the agent. We can evaluate the intelligence of these agents by their abilities. So, for example, if I have a robot and I want this robot to move from this point to that point, but instead the robot goes there, so it is not intelligent because of the goal that I have for this particular agent. So now we'll talk about the different cases of agents in deterministic and stochastic contexts. So a deterministic context is about something similar to the game of chess. So in this board, you can only apply certain movements according to certain pieces. You cannot do something different. Everything is so closed, so deterministic, okay, in the game of chess. So the uniqueness in the agent's current state completely determines its next state. So the idea is to create an algorithm to solve the problem. When artificial intelligence began in the 1950s, everything was about deterministic contexts. Everything was about rule-based artificial intelligence. Just like this. Here I have a very simple example. We have rules at the left-hand side. Let's see here. While not home, so the objective is to move this robot from this point A to that destination there, okay? So we are applying very deterministic, a set of deterministic rules to fulfill this goal. While not home, go. If you hit a wall, move to the right. If wall, move to the left, and then to the left. If you find a key, then get the key, okay? So this is deterministic. You just have a set of deterministic rules, and you want to find a solution in this closed environment, okay? So if you keep moving, in the program, if you keep iterating, at the end, you will reach the goal, okay? So that is the idea with a deterministic solution in artificial intelligence. So artificial intelligence, as I mentioned before, began in this way. It was like that in the 50s. However, life is not as easy as this. We are going to see some more complex examples, okay? So we can see that in this simple case, in deterministic context, a designer is required to define the initial rules of a computational agent. So you see, instead of using this as an argument against God, such as we saw in this quote, no, we can use computer science to demonstrate that a designer is necessary to be behind the creation of these rules. This is another very simple example of a deterministic context. So we have two values, two variables, and we want to print out the addition of these two numbers, okay? So always you will get the number 15. You will never get 16, 17, no, always 15. It is deterministic, okay? Deterministic. So, but what about this case? Let's say that you have an autonomous vehicle, Tesla, with autopilot. And this Tesla moves from the United States to Mexico or to Canada. Traffic lights there are different, yeah? In some states, you can see these differences. So what will happen with the autonomous vehicle in those cases? The autonomous vehicle has to do something. So This is the kind of problems that you find in the open world. Situations like this, uncertain situations, the unknown. Okay, so in order to solve these kind of problems, we have to move from these deterministic solutions to stochastic solutions. So a stochastic context is random in nature, uncertain, unknown, which is not unique and cannot be completely determined by the agent. The algorithm learns a solution to a problem based on data. And this is the area in which artificial intelligence has been very successful in the last years, in this area. Because we create programs that find a solution based on what? On data. And artificial intelligence, the universe of artificial intelligence is big. But one of the most exciting fields nowadays in artificial intelligence is called machine learning. Machine learning. So the idea with machine learning is that machines learn with data. According to this definition from Herbert Simon, learning is any process by which a system improves performance from experience. And when we talk about experience, we are talking about what? Data. Experience is data. And that's why big data, have you heard about big data? So big data is a concept, it's a field of study that is very popular nowadays, because if you have the data and you have the computer power, you can create these very intelligent machines. And this is a definition that I like very much about machine learning. It is the study of algorithms that improve their performance P at some task T with experience E. Okay? A well-defined learning task is given by PTE. So this is a classic example that requires machine learning. This is the task. Discover the numbers, handwritten digits that are number 2. Even for humans, for us it's difficult to discover, is it a number 2? For some people, yes, this is number 2, believe it or not. But even for humans, it is hard. So if we want machines to discover the number 2 here, what to do? How to do it? Okay, so let's use machine learning for that end. So according to this definition that we have here, a well-defined learning task is given by PTE, performance, task, and experience. Okay, so this is the task that we have. Improve on task T, so recognize handwritten numbers with respect to performance metric P, percentage of numbers correctly classified, and based on experience E, a database of human labeled images of handwritten numbers. Okay, so this is our task. Let's see how we can achieve that with machine learning. So machine learning, this is another definition that I like very much as well. This is one more of the fathers of artificial intelligence, Arthur Samuel, in 1959. My father had 9 years old at that time. It was a long time. So field of study that gives computers the ability to learn without being explicitly programmed. Okay, so how to solve this problem with an approach that is deterministic like this? We cannot. Classical computation or programming is like this. You have input, 5, 10, for example. You have a function, an addition, and then you have an output. Okay? For simple problems like this, it's fine. But how to apply this classical way of computing to this? No, we cannot. We need something else. So how to do it? Okay, with machine learning. This is the basic idea of machine learning. If you get the idea with this, you can go home and tell your family members, hey, I know how artificial intelligence works nowadays. This is the idea. Okay? So let's say that you have an input number. You have it in a piece of paper, for example, and you write it here, number 2, boom. And you want the computer to recognize this number 2, okay? An image, okay? So the function in this case is a machine learning that had been trained previously with images, a lot of images. You train this model with images, okay? And as an output, you don't get a specific value. You get a set of probabilities, okay? Probability of this, of being number 1, very low probability. Probability of that image to be number 2, 91%. Probability of this, of being number 3, very low. This is how artificial intelligence works, based on probabilities. It's not deterministic. That's why when I come into a Tesla car with autopilot, I don't feel 100% confident because you see there is a chance of error. Yeah, they don't make it public, you know. They don't say our accuracy level for these vehicles is this. They don't say that. Okay, but here you can see that everything is about probabilities. Okay? So this is an example of a research project I did with one of my students some years ago. We wanted to support the diagnosis of glaucoma. So glaucoma is a very bad disease. So many people suffer of glaucoma around the world. So the idea of glaucoma is that you see properly, but suddenly you start losing, your eye field, and finally you see a little bit, and poof, nothing. Okay, you don't see anything. So the idea is to help medical doctors in this diagnosis of glaucoma. So here you can see that, for example, these spots, very ugly spots, are because of glaucoma. Okay? So the result, the output that we expect is to get a probability of glaucoma or no glaucoma. Okay? It's basic. So how did we do that? So in order to create this machine learning model, we created an artificial neural network. So this artificial neural network imitates the basic structure and functionality of our brain. So here you have artificial neurons, okay, that are connected to each other. And at the end, you get the result that you want. So in each one of these layers, just like in the visual cortex, you remember this morning we listened to a presentation about the visual cortex? So we have different layers. So in different layers, we apply different mathematical computations until we achieve something like this, okay? So in the first layers, we detect very basic patterns, and here we detect more complex ones. Okay, so this is how we do it. Of course, we don't fully understand the brain, but we know that we as humans, we have neurons and we have connections or synapses among neurons. So, and the results were very promising. Here you can see the results for pictures without glaucoma, healthy images, and pictures with glaucoma. And here you can see the accuracy level, which is high. As closer to 1, the better. And it was a good result then. Thank God. Now let's talk about another approach. So in this approach, we use artificial neural networks, but this is not the only approach we can use in artificial intelligence. There are several approaches in artificial intelligence. So another approach is called genetic algorithms. Have you heard about genetic algorithms? Genetic algorithms have been used by some people to defend the idea of the theory of evolution, natural selection, okay? The interesting thing is that genetic algorithms work in computer science. They work fine. But I will explain later on how this approach cannot explain how life happened, okay? So, for example, genetic algorithms were used some years ago by NASA to create this antenna, the design of this antenna. And you can say, but it looks like kind of strange, but it works. This is the best design. So after several iterations, this algorithm, discovered that it was the best way to organize this antenna for this particular spacecraft. Okay, and genetic algorithms have been also successfully used in the design of microchips. Microchips have so many components, okay? Different paths. How to organize all these components in a very small piece of technology. And if you don't organize this well, it will become very hot. It can be broken, easily if you don't organize these components fine. So genetic algorithms have helped scientists to organize these components in microchips. So these are the basic rules of genetic algorithms. So first rule, selection rules that select the parents that contribute to the population at the next generation. So this is about natural selection, okay? Second rule, crossover rules that combine two parents to form children for the next generation. Third rule, mutation rules that apply random changes to particular parents to form children. So let's understand these rules, okay, with some examples. So initially, we have an initial population, okay, this is the population, and we have chromosomes, so chromosome A1, A2, A3, A4. Our genetic information is just composed by zeros and ones, okay, binary. Okay, so inside this chromosome, we have genes. So gene with value 0 or with the value 1. Okay, so an important aspect in genetic algorithms is the selection of parents according to the fitness function. Okay, you have heard about this, in the case of natural selection. So the goal, let me give you an example. Let's say that we have a goal to optimize the design of a car for fuel efficiency. So a fitness function in this particular example measures a car's fuel consumption over a set distance. So the car designs that consume less fuel will have a higher fitness score. Okay? So we use this fitness function to decide which cars we are going to choose to combine and create a new generation. Okay, this is the idea behind this fitness function. So this is how we do it. Let's say that we have chosen, according to the fitness function, these two chromosomes. So the next step is to define a crossover point. Okay, and we use this crossover point to know that we are going to combine some genetic material. Okay, so these ones are going to move to this side, and these zeros are going to move here. Okay, we swap them. Okay, and this is the result. In a new generation. Okay, in order to add new genetic information, the next rule says that we can mutate these values. Okay. So this 1 can be 0, this 0 can be 1. This is a random process to add new genetic information. Genetic algorithms have been used, for example, to solve the problem of the traveling salesman problem, or TSP, which involves a traveling salesman who must visit a certain number of cities. Have you heard about this problem? Yeah? Okay, so this is a very complex task. The task is to identify the shortest route for the seller to travel between cities. The seller can start and end in any city, but must visit each city once. The seller cannot visit a city more than once. So we have a lot of constraints. Okay, several constraints there. If you try to apply classical programming approaches, such as deterministic approaches, you will end up with something like this. With one city, we just have to program one step. 2 cities, 1 step. 3 cities, 6 steps. 4 cities, 24 steps. With 50 cities, you have to program all this. It's huge, So trying to apply a brute force approach to solve this problem is crazy. Not just in terms of programming, but also in terms of computer power. The computer has to process all this. It's too much. It's too much. So the problem scales factorially with the number of cities. the factorial of an arbitrary value, n is given by this, okay? M multiplied by n minus 1 multiplied by m minus 2, and so on, okay? This is the factorial. So this is a very complex problem. So take a look at this. In order to solve this problem, I wrote this program. Do you think that a program like this can be created just fortuitously, by chance? No. It was a designer, myself, who took these basic rules and applied these rules to solve this problem. Okay? An intelligent design behind genetic algorithms, for example. So programming a solution based on genetic algorithms is not a trivial task. You need to think very well about how to apply and program your rules. Although genetic algorithms help discover solutions to complex problems, they cannot, and I want to make sure of this, they cannot be used to explain how life originated, okay? They depend on pre-existing genetic information, for example, zeros and ones, rules, you have to define the rules, and a fitness function, which is a goal-directed nature. The message that I want to transmit to you in this afternoon is that a designer is required to define the initial rules, whether with genetic algorithms or neural networks or whatever artificial intelligence algorithm or approach. There is a designer who needs to define these particular initial rules in this stochastic context. Let me give you another example. This is about the dynamic adjustment of systems, okay? The idea with this is to imitate nature. So in nature, you have organisms like this, just such as the chameleon, that according to situations in the context, they change colors, okay, to defend themselves and so on, okay? So that is the idea with dynamic adjustment of systems, that these systems can modify themselves at runtime. So this is a very basic abstraction of a software, a system. In a system, you have some functions that are inactive, some others are active in a particular time set of time, okay? So at runtime, you can use some internal mechanisms so the system by itself adapt. So some of the initial functions that were active will become inactive and so on. So for example, if some of the function, or if you realize that there is let's say a security attack, let's say a hacker is trying to attack your system, the system can self-adapt in order to defend itself. Okay, that is the idea behind dynamic adaptations. And also, the system can evolve, not as in the theory of evolution or something like that, but can grow or shrink in order to defend itself or to become more efficient. So, how to reach all this? Do we need a designer behind all of this? The system is acting by itself, is defending or is trying to become more efficient by itself, but what about a designer? Okay, in order to do this, what I did, this in one of my publications, I proposed a variability model that shows the structure of the different functionalities of our system, and here we have different resolutions. So according to particular situations in the context 1, context 2, context 3, the system triggers different actions. For example, it will activate a functionality B or a function B or a function E and so on. Just with these two components, variability model and resolutions, you get this set of configurations. And here you see all the complexity that you have, all the configurations that you get just with these two. But initially, this is the idea that what I want to transmit here. You need a designer to create this. This cannot happen by mere chance. You need an initial set of rules. Okay? Moreover, in terms of software architecture, you need to monitor the system. You need to analyze the situations that you see in your system, in your context. You need to plan an adaptation and execute the adaptation. All of this is not mere chance. All of this is something that was created by an intelligent designer. So a designer is required to define the initial rules and mechanisms for dynamic adaptations. So in any engineering project, design comes first and then construction follows. In the case of creating intelligent computational agents, engineers have to follow a strict methodology to collect the data that are going to be used to train the models, prepare and clean the input data, create or reuse an artificial intelligence algorithm, for example, artificial neural networks, develop descriptive or prescriptive models, test the model to measure its quality, and deploy the model. It's not easy. It's not easy. There is a methodology behind the creation of these agents. Every step involves extensive reasoning and complex construction, as we have seen. And this is the picture of Conway when he was young, when he created in the 70s the game of life. Remember that I began this presentation telling you about the game of life. And this is an article that was published in 1970 in Scientific American. Take a look at what is said there. During the construction of the game of life, Conway chose his rules carefully after a long period of experimentation. Now let me go back to what Stephen Hawking and Leonard Bloodinow said. The example of Conway's game of life shows that even a simple set of laws can produce complex features similar to those of intelligent life. Who created these rules? Conway. We saw it, Conway. After a long period of experimentation, who created the rules? So they said, a very simple set of laws can produce complex features similar to those of intelligent life. As in Conway's universe, the laws of our universe determine the evolution of the system. Who created the laws of the universe? Does artificial intelligence just happen by mere chance? Genetic algorithms and artificial neural networks and so many other algorithms, super vector machine logistic regression, all these. You need a designer behind these rules that are created by someone, an intelligent designer. So let me finish with this. These rules are not, and in the case of Conway's game, were not the result of mere chance. In fact, in order to create intelligent computational agents able to produce complex features of behavior, it is necessary to establish the rules that govern the game, no matter how simple they are, just as in the case of Conway, with just 4 simple rules. The rules need to be established by someone. It can be said with confidence that rather than contradicting the need for a designer, intelligent computational agents, and artificial intelligence in general, are a great example of intelligent design. God is the designer of the laws that govern the universe. And I will finish with these 2 powerful Bible verses. First one, in Job, do you know the laws? It is God asking Job, do you know the laws of the heavens? Can you set up God's dominion over the earth? We don't know the laws, we know some things of the laws, but what about, what is behind the laws? The mysteries of the laws that govern the universe, we don't know. And this is a very precious Bible text in Jeremiah chapter 33. It is Jeremiah at the jail. The enemies were surrounding Jerusalem. Everyone was afraid. It was a very bad situation. And God is talking to Jeremiah, and he's saying, this is what the Lord says, if I have not made my covenant with day and night and established the laws of heaven, it is God himself saying that he has established the laws of heaven and earth, Then I will reject the descendants of Jacob and David, my servant, and will not choose one of his sons to rule over the descendants of Abraham, Isaac, and Jacob. For I will restore their fortunes and have compassion on them. After some years, what happened? God fulfilled his word. And he was saying, as I created the laws of the universe, I will fulfill my purpose in your life. God is reiterating here the promises made to demonstrate his determination for restoration. So if you're interested in this topic, I encourage you to purchase this book. This is in the ABC. My presentation, the presentation that I gave today, I published these results here on this book. Okay, so you can find it there at the ABC. 51 scientists explored evidence in nature. Thank you.